Okay, we're back again, and I'm going to go through this second example, which is now a true 3D vector problem. So we have this component here shown on the right. In blue, it's on a rod here, shown in green. We've got this force applied at the end here, and we're asked to determine the moment of the force about point A here. So our plan, so you should always stop and think about your plan for how you're going to solve the problem before just diving straight in. Think about the different ways of solving it. So what we're going to do this time is to write the force and the position vector in vector notation and determine the moment about point A by using the vector cross product. All right, so fortunately, we're given all of the direction cosines for each of these angles here. So these angles here will give us the direction cosines. If you don't remember direction cosines, then you might need to go back to your maths modelling 1 or physics to review that. And in the textbook, there's, and in the week 0 module for this subject, there's some material there to help you with that. Anyway, so basically what we need to do is to find our components in the directions X, Y, and Z. So, so along here, and up here. And it's easy in this problem because as I said, we're given these direction cosines. If we're not, then we've got to do a bit more work, and it's a bit more of a difficult problem. But in this case, we can just simply go 500 cos 60 for our direction in the X direction, and it will be negative. And then in the Y direction, 500 cos 60. And so what we're looking at is that that we're given the angles between the force and the axis that we're looking at. And then in the Z direction, angle between, let me get my laser pointer back, direction between the force and the Z direction is given is 45. Okay, so we just need cos of all of those. So there are our direction cosines, if we do those maths. And then take the 500 out the front and put in our vector notation, ijk, and that's what we get when we do our maths and use our calculators. All right. So our position vector goes from point A to any point along the line of action of the force. Hopefully, obviously, the simplest place to do that is to go to the point of application of the force. Right. So where you've got in the X direction, it goes from A to B minus 150. So again, I've just converted millimeters to meters here in my calculations. In the Y direction, goes from A to B 300 millimeters in the Y direction, and in the Z direction or K direction, we go from A up to B, so that's 100 in the positive K direction. All right, so that gives us our position vector. All right, so this time I'm going to use the determinant method. So to solve this cross product, we can use our determinant. We've got ijk across the top here, and then the top row, and then our position vector in the second row, and our force vector in the third row. Evaluate our determinant. So I've just put in the values that we calculated up here down into that determinant. And this time, instead of multiplying every term through, I've just used that equation for evaluating the determinant that I showed you a few slides ago, right, in the previous video. If you're not familiar or comfortable with doing this, you can just go and multiply through like I did previously, and then where you get I cross A I cross I, j cross j, and k cross k. They all equal to 0, and then you need to make sure that you're getting the right terms when you do the I cross j, j cross k, etc. Okay, so but we'll just use this method this time. So you can just write down that formula, remembering the minus sign out the front of the j term. Do the maths and sorry, I hesitated there because I was kind of still thinking about the previous problem. Right, why have I got I's and J's here? Because right, this time the direction of the moment is not just along the Z, X, or Y direction. Okay, so the vector, and we'll look at in a second the direction of this moment that we've calculated. Right, so when we get an answer like this, we can look at it and go, right, okay, well, that's the answer, and move on. But really, you shouldn't do that. You should stop and think about what's going on. Try and get a feel for what these numbers mean, and whether they make sense in terms of what we've got here. Okay, so and particularly whether you got the signs out the front correct or not. Right, so let's have a think about this. All right, so we've got this first term is the moment vector in the x direction. So we can see that's going in the positive I or the positive x direction. So we put that there. So really what I'm drawing here are essentially the components of the moment that we've calculated. So then we've got minus 28 in the y direction, so out here, and then plus 37.5 in the k direction. So our vector moment looks something like this. Okay. So along the x, minus y, and then up in the z direction. Right, so if we think about our right-hand rule and think about the direction of rotation, right? If we put our thumb along the direction of the moment, and our fingers should point in the direction of rotation. Okay, so we can see how it looks like that. So that's our direction of rotation. So hopefully that's starting to make a bit more sense, right? And we're starting to get a feel for, okay, this, right, I can understand what this means now. But let's have a look at some other things here. So some other considerations, right? What we should see, right, is that the moment vector is perpendicular to the plane formed by the position vector and the force vector. Okay, so if we put in that plane here, this moment here should be perpendicular to that. And it doesn't really look like it in this picture. This looks a little bit flatter than it probably should be, but yeah, that's where the difficulty, or it's one of the difficulties comes in trying to visualize and understand these 3D diagrams. This is supposed to be 60 degrees here. So in this direction, kind of looks more like 30 degrees than 60. So, this plane would actually be sitting up a little bit more vertical, right? Which would indicate that this this moment vector is correct. You could try, drawing this in the three planes. So do, front, top, and side views of this, like you did in Intro to Mech in your drawing, when you're doing drawings, and draw it to, roughly to scale, and you get your angles roughly right, and see that this vector moment is, 90 degrees to this plane. Or you could do a SolidWorks model and do that. All right, so let's consider a few more things here. So some practical implications of this. So let's consider firstly this term here, the 81.1i, which indicates a moment about the x-axis. Right, so what is that practically? Right? Practically, that's the moment that's tending to cause this component AB to rotate about that rod. Okay, so so we've drawn this component here of the moment along the direction of the rod here, and if we put our right hand rule, put our thumb along the direction of X and rotate our fingers, we can see that that's makes sense, right? That this is going to be positive, right? We've got this force up here. You can probably see that it's tending to cause it to rotate around this way. Yeah. All right, so this thing's not going to be in equilibrium, right? Because there's nothing to react against this moment. All right, what else do we got? Let's look at the next term. I've drawn the moment in here for you, or the component of the moment in there for you. All right, so let's look at the next one. So 28J, so this is a moment about the y-axis going in the negative direction. Okay, so if you put your thumb along the y-axis in the negative direction and rotate your fingers, you can see, yeah, okay, that looks like that's what's going to happen. It's going to tend to rotate that around there. Okay. And that is going to cause a bending of this rod here about the y-axis. Okay, so if you've got this sleeve over this rod, and this has got some length to it, then we're going to cause bending in this slide. So if this is long and slender, I lost my long slender rods, it's going to cause a bending like this in the rod. Didn't anticipate doing this demonstration in this video, but okay. Hopefully you can see that's going to cause, if we're trying to rotate this thing, this blue thing around the y-axis, and there's some length to this collar, it's going to cause that rod to bend. Okay, and then when you're doing a design of this thing, right, you'll need to design the diameter of this rod to be able to cope with that bending, right? And you have to calculate the stress due to bending, which we'll do later on in this subject. And then I've just shown that vector component in there. And then thirdly, we've got the moment about the z-axis, about the z-axis. And again, that's going to cause some bending of this rod, right? If this has got, right, there's a force here tending to rotate this blue component about the z-axis, and it's got this rod going through this collar, right? That's going to cause a bending of this rod. And again, we'll need to design this rod to be able to withstand that bending moment. Now, the other consideration is that equal and opposite of this bending moment will be an internal bending moment in the component AB. Okay, so there's going to be bending and stresses due to bending generated in this blue component here. Okay, which again, we'll need to make use of in order to design the size of this component appropriately, which we'll do as we go through the subject. And similarly, we've got an equal and opposite of this moment here causing bending of the rod. There'll be an internal torsional moment. Okay, so if we grab this sticking out here, so that's going to cause a twisting I'm not sure if you can see me in the little picture in the side, but there's going to be a twisting of that flat plate there that we'll need to take into account when we're designing the size of this component. All right, so that's the end of that example. It took a little bit longer than I expected it to, but doesn't matter. Well, hopefully you found the extra discussion and considerations interesting and helpful, and help you to see a little bit beyond just the maths and the cross products and so on, to get a feel for how it all fits into the design of mechanical components. All right, see you in the next video. Bye.